Okay, good morning everybody. I hope everyone's having a wonderful day. So today I'm going to be talking about properties of asymptotic notation. So I've asked you previously to review the notes I have for this. So I'm going to be going a little faster and I want to provide mostly intuition for what I'm discussing. And if we have time after this, my plan is to start moving into discussion about lower bounds. So I'll talk more about that later possibly. So I just want to first just reacquaint you with some important classes of complexity functions. So class is a fancy name for our purposes. It's just a set of functions that all have the same type. In our case, they're complexity functions. So you may be acquainted with some of these, and I've already talked about them with respect to big O already, and I told you that these are sets of functions, right? They're sets of complexity or growth functions. So these are just some ones that you may have heard of before. I just want to reacquaint you with them. So you may know, for example, big O1 means constant, big O of log n means logarithmic, big O of n is linear. A couple that are going to be more relevant towards later parts of this class are polynomial. So if this is some constant c, we call that a polynomial. And if it's c to the n and c is some constant bigger than 1, we say that this is exponential. So these are just some ones just to be keeping in mind. I've tried to list them in the order for which the sets are contained. So for example, big O of 1 is contained within big O of log n, big O of log n is contained in big O of n, and so on, for appropriate values for c down here. So is everybody fine with that? I'm sure you probably heard of these before at some point, but I just want to make sure, just in case, that you've seen this terminology before. If you haven't, there it is. So now I want to switch gears. I want to talk about properties of asymptotic notation. So I'm going to let f, g, and h be complexity functions. Complexity functions. And for your purposes, you can just oh, what's big O n to the n? A really bad time. Okay, that's just a joke, but I'm not really quite clear if there's actually a name that the community generally uses for this one. I don't know of a name I usually use. I just say, yeah, it's big O of n to the n. But it's a really bad time, because keep in mind that this isn't just like, okay, well, it's like 2 to the power n. No, this is like n. Remember, n isn't a constant in respect to this set of functions here. So it's something that isn't a constant raised to something that isn't a constant, which could get really, really big. Because keep in mind, already things like 2 to the power n are exponential over here, and that's strictly contained within big O of n factorial. So like we're talking about something really big. You're going to be in for a really bad time if you're trying to determine if that's going to be efficient or not for you. It has to be something very special. But yeah, I'm not aware of a technical term for that last set there. Sorry, I almost tripped here. That's pretty epic. But yeah, so hopefully this helps a little bit. I just call it big O of n to the n. It's so I'm going to consider f, g, and h. For your purposes, you can just assume each of these properties holds for big omega and big theta, unless otherwise stated. So unless otherwise stated. So I'm going to just give you a bunch of properties. I'm going to give you some intuition of why either they're true or where you may encounter it or may apply this property. So this is hopefully going to help accompany what you've been reading. So I'm just going to kind of go through some general rules. So I'm going to start off with one that at first seems rather trivial. It's what is called reflexivity. So reflexive, as you can tell, today's been a wild day. Reflex. Let's just rewrite that. That's reflexivity. There we go. My apologies. Reflexivity. So if I tell you that I give you f, I could tell you that's big O of f. That's what it just means. That means if I have the thing, it has the property. So that's all it really means. So if I give you a complexity function, I know that it's going to be the thing. It's going to be big O of f. So can anybody tell me, just you can think off the top of your head, what constants of C and N0 would work to prove this property? Now remember, it's any complexity function. It's not just like some fixed one I did like I was doing last time. Can you think of two constants, the C and N0, that would work here? Does anybody have any ideas? Yeah, N0 is equal to 1 works quite well. What would I pick for C with that to accompany it? So think about it. I want to show there's C and N0 such that for all n greater or equal to N0, f of n is less than or equal to C times G of n. Now, so yeah, if you pick C is equal to 1, then you know, okay, well, the two sides of the inequality are equal, right? So for all n greater or equal to 1, the inequality holds, hence proving this claim. So yeah, so those would be two constants you could use to prove this claim. I'll give an example of actually like proving some of these properties. So I'll probably do one or two today. Just so you get a flavor for this, there are all these proofs. So any proofs that I haven't mentioned here, with some exceptions, like this one, because I just talked about it, are in the notes. So if you're wondering, oh Dan, what's the proof for that? It's in the notes, most likely, with one exception. So another property. Now I'm just going to sort of frame this in a couple of ways. So the first one, this is one that you might be familiar with. Constants independent of the input do not matter. So that's the kind of the first rule. Do not matter. So constants independent of the input, and that says do, sort of melted in the microwave there, do not matter. So that's property number 2. In terms of discussion about big O, what I'm saying is if k is a positive real number, and you know that f is big O of g, then k times f is big O of g. So there's two ways that this property, of course, creeps in practice. There's two ways you can think about this. Okay, first, imagine if I had, so I'm going to give you two scenarios that are very real things that can happen. First one is one for which that can happen in, say, if you're programming or you present me an algorithm. And that algorithm invokes a method or a subroutine or a function, whatever you'd like to call them. And it does this a constant number of times. So for example, imagine you have some subroutine and you know it takes big O of g. So it takes big O of g to execute. And you find out, hey, look, this algorithm invokes that subroutine some constant number of times, say twice. What you can conclude from that is that, okay, well, if the original one took big O of g, that means that when I run it twice, it's still big O of g. That's one way you can apply this rule. Another one, of course, we've already seen it when we were doing our accounting operations, when we were doing our analysis for algorithms. Remember how I told you, okay, well, I have a bunch of constants. Well, those constants end up being negligible in terms of the big O notation. Because the big O notation, there will always exist some constant I can select that's big enough that's going to allow me to prove the big O claim, right? So I have like C1 times n plus C2 or something like that. Well, when I prove the big O claim, what I usually do is I say, okay, well, there exists some C. Well, that C right there is going to, like, the way you'd select it is so that it will cause the right-hand side of the inequality to dominate your complexity function in question. So when you see that constant is K here. That's one way you could think about that. More practical terms, because it's not very easy to think about this in terms of proofs all the time, a practical way you can think about this is I tell you that, say, some primitive or elementary operation takes constant number of operations. Well, what is that? Some constant number of operations is really just big O of 1, right? It's constant. So, but what is that in that scenario? Well, that just means that, okay, if some of my operation is some constant number, like C1, then I know G is big O, well, it's some constant function, like 1. So it's big O of 1. But that means if I have some constant number of operations, that means it's still big O of 1, right? This is why very often in our analysis, we treat those primitive or elementary operations like one step or one operation. So that's how you can this can creep up in you're working in practice, or whether you're doing something more like an analysis. Is that there's two ways. You can think of it like I run the subroutine many times, but I have it some constant number of times. Or it could be, hey, look, I have a bunch of operations that happen. All of them take constant time, but there's a constant number of them. That's all going to take constant time. So those are two ways I can motivate the invocation of this rule. Are there any questions about this? So I just wanted to give some discussion just to clarify where and how you might use this. There's a lot of ways you can use this. Generally, if you have a complexity function, you have it like C1 times n plus 5 or something, you know that the C1 and the 5 don't really matter a whole lot. It's just really the n that you really care about. These are constants independent of the input. The input in this case would be n. Are we all good with that? I have the proof for this in the notes if you're curious. Okay, I think we're good. So I gotta underline that just to really emphasize that that's the rule I'm talking about. Another one, actually, let me go to this board over here. So another rule that you should be aware of is that you can take the largest function over functions in a sum. So take the largest function over functions in a sum. So what do I mean by this? Let me just elaborate. So what I'm saying is that if I give you f and I sum it with g, that this is in fact big O of the max of f and g. So imagine I give you, this crept up a little bit earlier on in the course when I was talking about usage of big O notation, where I had a bunch of terms. I had like n squared, and I had an n cubed. And I wanted to know, okay, well, what's the big O in that case? So how do I determine that? Well, you know that, okay, so like this, imagine if this was n cubed and that was n, for example. If I sum over, say, two of these, like n cubed plus n, by reciprocal, you can keep applying this rule over and over again if you like. You can have, say, 3 terms. What you do is you use this once and then you invoke it again as another property. So what you would do here is you would just say, okay, well, that's n cubed plus n. All it's saying is, okay, so you take the maximum of those two things. Okay, n cubed or n. But remember, n cubed is always larger than n, right? For all n greater or equal to 1. So that means that this would collapse into just being big O of n cubed. So you might ask, Dan, how does this come up when I'm actually doing stuff? So I want to come back to the example that I did when I did the usage case, where I had, imagine you have like 3, in our case, we'll just say 2. We have 2 subroutines. So subroutine A and subroutine B. So say this is subroutine A. Subroutine A, and this is subroutine B. So So I want to talk about the complexity functions. These are the representations of those complexity functions for these two. Imagine I do worst case analysis on each subroutine, and I derive f, and I also derive g. Now, you may have encountered this rule before in some other vein, but the way you can think about it is, okay, well, if I know that this one, in terms of the complexity function, dominates g, then you know that g doesn't really matter a whole lot with respect to big O, right? It's because the running time of subroutine A dominates the running time of subroutine B. They may be the same even, but the point is that if I say, for example, subroutine A was something like, I don't know, like we had n cubed, and say this was n, if I was counting up the number of operations, it may be some constant times this or some constant times that. The whole idea is that this rule is telling you that subroutine A's running time is going to dominate when you do all of the operations among both. That's all this is saying. So you just take the largest function over all the sum of functions. So the easy way of describing this in terms of programs is if you have a really expensive running program, or subroutine in our case, and then you run one that doesn't take as long to perform, it has less operations in the worst case, the one that's going to take the longest is the one that's going to conquer and take over the big O term, okay? That's all I'm saying. Is that clear, everybody? Are we all good with that? So you may have encountered this when you think about, say, you have two subroutines, you do the first one, then you do the second one, and okay, well, what happens with the worst case time complexity? Okay, well, the one that takes the longest, it ends up being the one that pops up into the big O. At least in the worst case. Are we all good with that? Don't be shy. Don't be shy. If you have any questions or you feel like, Dan, I don't like what you just wrote on the board. I don't like that at all. You have to let me know, okay? Are we all good with this? Don't be shy. But I'll let you think about what I was describing here. There's many ways you can use this rule. And I have the proof in the notes. So one that is closely related to this one is the following. So adding two functions of the same order produces a sum of the same order. So this sounds kind of like what I just described previously. It's quite similar. Let me describe it a little bit more formally for you. So if f is big O of h, and g is big O of h, then f plus g is big O of h. So imagine I know that f takes big O of h, and I know g takes big O of h. When I sum over both, when you think of sum in this way, think about it like I'm executing the algorithm for which the complexity function is f. And imagine I have another subroutine or something that is going to be represented by a complexity function g. And I know that runs in big O of h. That means that if you executed A and then B, and you know both run in big O of h, then the result will run in big O of h. That's all this is saying. So I'm going to prove this one for you, because I think it's important that you see one of these that's a little bit more involved. Are we okay with this property? Are we okay with this? So everybody understand the statement? Because I'm going to prove it. Now, the big trick here, okay, Is it f of, it's f of n. Yeah, it's f of n. My apologies. Yeah, it looks like an h, it's an n. It's an n. Yeah, it's an n. It takes me back actually to my undergrad. I used to have a professor I dearly liked a lot, but he made his n's and h's look almost exactly the same, and he wrote in cursive. Love the man, but it was just, it was fun taking notes from him. Especially when you take a class where almost everything is either an N or an H in terms of the notation. Okay, so we're going to try proving this claim together. So let's do a proof for this claim. Now, of course, you could use other properties to prove certain big O properties, but I'm going to keep things fundamental. So I'm just going to use definitions to directly prove the claim. So I'm going to not require using other claims to do this job. Now, as somebody points out in the chat, if you're clever enough, you can use property 3 to prove this one. But I'm just going to keep things bare bones down to the point because it's the first one I'm showing during class. And this is the same way I have it in the notes if you're curious. So I'm going to say to prove the claim, we determine constants. So remember, this is just the same game plan we've been doing this entire time, right? I just tell you what I'm going to prove. If I want to show that f plus g is big O of h, that means I need to find two constants, the c and the n0, such that the inequality of question holds. I'll write that on the board. We determine constants c, which is a positive real number, and n0, which is a positive integer, such that f of n plus g of n is less than or equal to c times h of n for all n greater or equal to n0. Now, remember, so this is going to be really relevant when you're working on the assignment, is that if I give you a claim like this and I'm given information in advance, so I really just need to hammer this in. So I'm going to move back over here so you can see the statement, so we can see how we can use the statement I'm trying to prove here. So I want to remind you, the statement says if f is big O of h and g is big O of h, then f plus g is big O of h. So what does that mean? So in our strategy, this is an example of something called a conditional statement. So I have if this and this, then it follows that this holds. So when you're proving a claim like this, you can use information that is a part of the if part of the claim to deduce the then part of this claim. So I can use in my proof that f is big O of h and that g is big O of h in my proof. But I'm going to use these facts to get me to f plus g is big O of h. Does everybody understand what I'm going to do next? I'm going to use these two facts, and because each one of them involves constants, I'm going to instantiate, or I'm going to create these constants out of that definition, and I'm going to do some fun hodpodgery to create some new constants that I could use to prove the claim. That's going to be the game plan. So I'm going to write that both f is in big O of h and g is in big O of h, implying implying there exists constants. Now remember, for this one, there is a C and an N0, right? But I already have C and N0. I already have names for these. I'm going to give new names for those constants. And because of this, there exists a pair of constants as well, another C and another N0. I'm going to give these names as well. So I'm going to use these. Implying there exist constants, C1, C2, which are positive real numbers. So C1 comes from this claim, and C2 comes from this one right here. So I'm just going to use these because they're part of the conditional, the if part. So that's those are from each one of these. I get a C, and I also get those N0 values. But remember, I already have an N0, so I'm going to give them different names. And N1, N2, which are positive integers, such that now I'm just going to write out what each one of these statements means, and I'm going to try to combine them in a meaningful way, such that f of n is less than or equal to c1 times h of n for all n greater or equal to n1, and g of n is less than or equal to c2 times h of n for all n greater or equal to n2. It was a mistake to segment the board this way, because I know I'm left-handed. It makes things fun when you're trying to read this thing off the board. It sort of makes things extra fun. So I have these two statements here. So remember, I get all of this for free because f is big O of h and g is big O of h. Does everybody understand what I just did here? I just invoked the definition of big O here, and then I invoked the definition of big O right there. And I've just labeled it nicely into a sentence such that it just tells me what each one means. So I'm going to use this information now to derive for me these constants. But I'm going to make an observation. By summing, so I'm going to use that, remember the last day I used that bucketing idea where I take the inequalities and I sum over them? And I say, okay, well, if everything on this side is less or equal to the thing on that side for each one of the inequalities, then it must be when I sum over all the inequalities, everything on the left side must be less or equal to everything on the right-hand side. I'm going to use that same strategy right here. So by summing over both inequalities, now I need to quantify this. When n is greater than or equal to the maximum of n1, n2, just to remind you, this is a max function. It just produces for me the larger of the two numbers that are sitting inside these curly braces. So all it's going to do is if, say, n1 is bigger than n2, it'll just give me n1. If n2 is bigger than n1, then it gives me n2. The whole point here is that you're going to see that I'm going to require, because remember, f and g, I don't know what they are. They're just arbitrary complexity functions. Likewise, h is as well. So I need to make sure my proof takes this into account. So when this is the case, I get the following. So I'm going to sum over each one of those inequalities. So I'm going to take this inequality and this inequality. I'm going to add them over each other. So it means I'm going to get f of n plus g of n on the left-hand side, and I'm going to get c1 times h of n plus c2 times h of n on the right-hand side. Does everybody understand what I'm doing here? It's very important. So that's why I say this. It's very important. So you're not seeing it comes out of the ether or something. So now I have this. I'm going to just rearrange the terms a little bit. Notice that I have c1 times h of n and I have c2 times h of n. Notice both of these terms have h of n. So I'm just going to factor this. So I'm just going to rewrite this as c1 plus c2 times h of n. Now, this should look really interesting to you because now I have f of n plus g of n is less than or equal to c1 plus c2 times h of n. Does everybody see that? So do you see right now what I should pick for c? Do you see what c might be? Hopefully the way I wrote it should make you very persuasive what c should be. I'll tell you, it's this one right here. So I'm going to pick c to be this. So by selecting constants, c equals c1 plus c2, and n0 is going to be the max of n1 and n2. The inequality f of n plus g of n is less than or equal to c times h of n holds for all n greater or equal to n0. So all I have to do at this stage is I just have to do one little thing here. I just got to give a conclusion, right? I have to attach everything together. Therefore, by the definition of big O, f plus g is big O of h. And we're done. But yeah, if you pick any c that's bigger than or equal to c1 plus c2, that will work. But usually it's nice when you can derive it directly like this, if you can. But remember, you just got to find one. That's all you need to do. Okay, so is everybody okay with this proof? Is everybody going with this? Because you might have to do something like this on the assignment. Okay, so if there aren't any questions, I'm going to proceed. I have a few more things to summarize, and then we'll wrap things up for today. So I'm just about done going through the list. Okay, everybody. So the next one I want to talk about is the product rule. Product rule of big O. So this is just imagine you have let F1, F2, G1, and G2 be complexity functions. So if you know that F1 is big O of G1, and you know that F2 is big O of G2, then the product of F1 and F2 is big O of G1 times G2. So that's what this property says. Now you might ask, Dan, so all I'm saying is if you know one is big O of this and it's big O of that, then the product of those two is big O of the product of the resulting ones in the big O. So you might ask, Dan, where does this pop up in practice? Think of nested loops. So imagine you have a nested loop. So just think of a nested loop. Like imagine you have like a for loop right here, and you have another for loop right here. So imagine you determine that inside this for loop, this takes a big O of G1. And this outer loop without considering what's in here, say you consider everything out here, not necessary, so I'll just say this, but without none of that. Say if I say that this is big O of G2, notice that if I take and I count up all the operations here, if this is big O of G1, then if I count up all the operations over the nested loop, which all the stuff that's happening out here, outside the loop is big O of G2, then it's actually the product of these two. So this is the natural place where the product rule creeps in. So if you're having a hard time seeing this, just think about the outer loop, say, going from 1 to n, and the inner loop going from 1 to n. Well, the inner loop goes and says, okay, well, this is going to be big O of n inside because it's going to perform n iterations. The outer loop is going to perform n iterations, but in total, all the operations will take big O of n squared. That's a direct way you can invoke this property. Is that clear, everybody? So I have a proof for that in the notes. Oh man, I'm gonna need one more minute. Is that okay, everybody? I just want to knock out one or two more things, but it's not going to be very long. Okay, so first, it's worth noting that a big O is transitive. So the transitivity of big O, all I'm saying is that if you know that F is big O of G, and G is big O of H, I'm hoping that's not going to be cut off on the board. So I have, if F is big O of G and G is big O of H, oh good, it's on the board, okay. Then you can conclude that F is big O of H. So I left the proof for you to think about. It's very related to your assignment, so that's why I'm not giving you the proof. So I'll let you think about that one. But I'm not going to say anything more about that. Another one I want to talk about just quickly, because there's just a couple of things about big theta I put in the notes. I think they're rather straightforward if you actually think about them carefully. So for example, big theta, for example, specifically is symmetric. So remember I told you that big omega and big O have a very close relationship. So if I say F is big O of G, this is equivalent to me writing that G is big omega of F. So if you could show both directions, as in F is big O of G, and you could show that F is big omega of G, then that means that it doesn't matter which order you put them in, right? So that's a property of big theta called that it's symmetric. It's also worth noting that if you want to convert between any two logarithmic bases, the base itself actually doesn't matter a whole lot. That's why computer scientists tend to just not write it down, or they just assume it's base 2. That's a fun fact. If you're curious more about that, you can always ask me sometime. I'm sure I have the proof kicking around somewhere. Other than that, I think I also mentioned about polynomials. It's just that same rule I talked about last day. But I want to just summarize one last one that should kind of help, like if you remember your calculus, I just sort of want to connect one small thing for you. So the last one is involving the limit theorem. Once I finish talking about the limit theorem, we'll wrap things up for today, okay? I apologize for going a couple minutes over here. Okay, so this is the limit theorem for asymptotic notation. Now I'm going to assume that you give me two complexity functions, and if I compute the limit, so if I compute the limit as n approaches infinity, now I'm not going to worry too much about technicalities of how n as an integer can tend to infinity, or anything of this nature. I'm not going to focus on that. I'm going to consider the ratio of f and n over g of n, and I'm going to assume that the limit exists. So I'm going to assume there exists some limit. So there's going to exist some limit. Then you could say the following, and I'm going to try to tie all of the asymptotic notation I've talked about up to this point. So this should give you a nice picture if you really you're just dying to use limits. You're welcome to use these. So if anybody has to leave, don't worry. The video will be up later today. So if you find out that the limit, when I evaluate this, it equals c, and c is equal to 0, then you can conclude that f is little o of g. It's also worth noting, because it's little o of g, you can also, this also implies that f is big O of g. So that you get this for free. So if you don't want to think about little o, just think it's big O. Just big O. So if c is not equal to infinity, then you can straight up assert that f is big O of g. Actually, just as a fun remark, if you're wondering, I mentioned Landau, the one who first kind of introduced the idea of asymptotic notations. When Landau defined what little o was, it's literally using this, if you're curious. But it's worth noting that whenever I ask you for the definition of big O, we're using the one that we're talking about previously, the one we've been using for all of our proofs. This is a property that we're going to use, but it's another way of thinking about all these things if you're familiar with limits from calculus. But I'm just mentioning this. I'm not really going to be too focused on you using this. I just want to make sure you're aware of it, because I know that you've taken probably some calculus before. And this is something you could easily do offhand if you really just need to check something. So if you know that c is between 0 and infinity, but it's not one of those either, then you could say f is big theta of g. You get big theta if you just find it some number that isn't 0 or it doesn't go to infinity. So if, however, c is not equal to 0, then f is big omega of g. So I want you to think about how this ratio operates when you think about these constants. So I want you to imagine as n gets big how the functions behave. So for example, in this case, if you know it's not equal to 0, that means that something on the top isn't definitely going to get so big that it's going to absolutely crush what's in the bottom. Actually, sorry, the other way around. I was just thinking about this for big O. But my point here, actually, I think I had the right way. But anyways, I'll let you think about that. If c is infinity, however, you can say that f is little omega of g, which obviously this implies that f is big omega of g as well. So the way you can easily use this, if you truncate these two cases and you truncate these two cases together, it's honestly a little bit easier to remember. But you may find this helpful when you're, say, doing some practical work and you really just want to say, hey, look, I just want to know what this looks like if I have the two complexity functions. You could compute a limit like this. Now, if you know anything about limits, you have to be very careful, though, because sometimes the limit doesn't actually exist, or you get an indeterminate form. With more calculus, such as L'Hopital or Hopital's rule, you can simplify down the limit into a special way, but I'm not going to cover that here. But I just want you to be aware that this exists. I'm not going to focus so much about it in this course, but I just want you to know it exists, and this is something very handy if you know your calculus. Is everybody okay with that? Are we all good with that? Perfect. So that's everything I have to say about asymptotic properties. But yeah, I mentioned a couple things about big theta while I was erasing the board. That's everything I have to say. So next time when we come back, we'll start talking about lower bounds, which is a pretty exciting topic. So I want to say thank you very much and have yourself a beautiful day. I'll see you later.